Hi. In this lecture, I would like to finish up the section 4.5, the derivative and the shape of the graph. Okay. Now remember in the first package, we have learned how to use the first derivative to define increasing and decreasing function and use the second derivative test to define the concavity of the functions. Okay. So this is actually is related to the first package, okay? And then now, after we learn how to take the derivative of functions, then I would like to continue to finish up this section 4.5. Now again, to your final, you will know that you will have the section 4.5 has one of the sections, okay, to take the test then. Okay, so then let us finish up this section now. Now, before we finish the section 4.5, I would like to talk about the mean value theorems. The detail is actually in the section 4.4. Okay, so the mean value theorems, what is this? Let f be a function that satisfies the following hypothesis. F is continuous at closed interval AB. Second, f is differentiable on an open interval AB. Then there's a number C in AB such that f prime of C equal to f of B minus f of A over B minus A. Okay. Of course, first of all, we know that this is actually is every way of change on the interval between A, B, right? And then now we could actually talk about that in between. Okay, so maybe let us look at this picture right here. So we have this one right here. This is actually is the slope of the secant line, which is every way of change between A and B. And by the mean value theorems, we will be able to find a point at x equal to C, where C is in between A and B, that the slope of the tangent line at this point, C f of C, is the same as the slope of the secant line between x equal to A and x equal to B. Wow, this is the idea, the mean value theorems, okay? And then what is the useful of the mean value theorems? It actually is we could use the mean value theorem to prove that f prime of x equal to 0, then f must be a constant. And f prime of x equal to g of x, then f of x equal to g of x plus c, okay? And then the detail is actually in section 4.4. You could actually check it out, okay? Now, also, let us look at the second graph here, okay? This is also the mean value theorems. Then, again, if the f function is continuous between x equal to a and x equal to b, then the slope of the tangent line, the slope of the secant line between x equal to a and x equal to b is the same as the slope of the tangent line at x equal to c sub a, c sub 1, and x equal to c sub 2 in this case then, okay? Okay, again, this is the mean value theorems now. Okay, then let's see how do we actually work out this mean an example here. We would like to use the graph of f to estimate the values of c that satisfy the conclusion of the mean value theorems of the interval for the interval between x equal to 0 and x equal to 8. Okay, so in this case, first of all, you will see that this function right here is actually continuous functions between x equal to 0 and x equal to 8. And also it is differentiable as well, because again, this is a smooth curve. Then in this case, we know that here, okay, then let's check this out. So I would like to find the slope of the secant line between x equal to 0 and x equal to 8. Wow, it's really hard to use a ruler. Okay, so then let's draw this out right here. Okay. Okay, so then first of all, maybe let us look at this one, every way of change between x equal to 0 and h equal to 8. is equal to f of h minus f of 0 over h minus 0. Then you will see that in this case right here, it is equal to 3 minus 0 over 8, which is 3/8 then, okay? And then now, what I would like to do is I would like to find f prime of c, which is equal to 3 over 8, okay? And then now, then you will see that in this case right here, that remember the c value is in between x equal to 0 and 8 and x equal to 8, okay? Okay. And now this is what we have. And then now if I move it, it seems that I have here, I have 1. I have another one is around here. And I also have one is about here. Okay. Okay, so then now we could actually check it out. The first one, C is about 0.3. Maybe I call it C sub 1 then. And then another one about, I just say that this is C sub 2, 2, 3, about 3. And then maybe I have one more, that's C sub 3. C sub 3 is about 1, 2, 3, 4, 5, 6, 6.2 then. Okay, so then this is actually is the idea about the mean value freedoms now. Okay, okay, then now let us look at the second example. So the second example is determine whether the mean value freedoms apply to functions over the given interval, in this case is x equal to 0 and x equal to 6. Justify your answer. Okay, so first of all, we notice that the function f is a polynomial function. So in this case right here, sin f is a polynomial, right? Then f is continuous on the closed interval. (0,6), okay. And 2, again, sin f is polynomial. And also, f is differentiable on the open interval. 0,6 then. Okay, so it is actually satisfy the two hypotheses. Okay. Okay. Then now, the exit, I would say that is by the mean value freedoms. That exceed a number C such that f prime of C is equal to f of 6 minus f of 0 over 6 minus 0 then, right? Okay, then of course, then let us look at the detail now. I know that f prime of x is equal to 3x squared plus 2, okay? So then in this case, f prime of C will be 3x squared it will be 3c squared plus 2 is equal to f of 6 is equal to 6 to the power 3 plus 2 times 6 plus 1. So it will be 216 plus 12 plus 1. So 228, 229 then, right? And then f of 0 is actually 1, okay? So I will have 229 minus 1 over 6. Okay. Then of course this is 228 over 6. 6 times 3, 18. 6 times 8. Okay, it's 48. Okay, so then now I will have 3c squared is equal to 38 minus 2. Then c squared is 36 over 3. Then c must be plus or minus square root of 12, right? And of course, in this case, now because again, we are looking for the interval between x equal to 0 and x equal to 6, then we will choose the positive 2 with 3 then. Okay. Okay, then now, and we know that 2 with 3 is in between the interval, the closed interval 0, 6 then, right? Okay, so then this is exactly how we justify, or maybe how we find the C value in this case, by using mean value freedoms. Okay, so now this is why I introduced the mean value freedoms, because again, when you get to like Math 152 or even higher level maths, from time to time, we are using the mean value freedoms to help us to prove some other freedoms or something like this, right? So therefore, I would like to introduce mean value freedoms right now. Okay, so when you see the mean value freedom again later on, then you will see what is going on then. Okay, but again, the main thing in this video right here is I would like to use the first and the second derivative to actually sketch the graph. Okay, using the technique like the first derivative test and the second derivative test, something like this to do it. But mainly we are using the first derivative then. Okay, so then now let us look at this. How do we actually use like the first and the second derivative, or just the first derivative, right? To help us to sketch the function then. Okay, so then now let us look at this one. So I would like to find the interval of increasing or decreasing of this function b. Okay, and then remember, if we want to find the increasing and decreasing, we need to work with the first derivative, right? We would like to find the local maximum and the minimum values. So basically, to this one right here, we are going to use a side charge. Okay, to do this. Then we would like to find the interval of concavity, which is to this one, we are working with the second derivative now, right? And the point of inflection. Of course, we're also using a side charge to help us to do this. And then use the information to sketch the graph, okay? Okay, then what I would like you to do is maybe you could actually pause the video and then try to work with the first and the second derivative. And then I will show you what we need to do to the rest of the problem then, okay? Okay, then maybe let us try to take the derivative first, right? Okay, so then here is my first and the second derivative of b, the function b. Okay, and then now, in order to find like increasing and decreasing, of course, we are going to work with the critical numbers now. Okay, so then we would like to find the critical numbers. Then remember, we could set p prime of x equal to 0, or b prime of x is undefined, right? Okay. Okay. Then now we could have 2 over q root of x minus 1 equal to 0. Then I will have 2 minus q root of x over q root of x. Then in this case, we could raise to the power 3 to both sides. Then I will have x is equal to 8. Okay. And then, of course, if I have b prime of x is undefined, then x must be equal to 0 then. Okay. Okay. And now we are going to work with the side charge now. Okay, so on this side charge right here, we will like to work with b prime, and then we have x equal to 0 and x equal to 8. Okay. Oh, by the way, I should start with this one. What is the domain of this b function? Okay, because again, when we try to sketch the function, of course, we need to know the domain of the function then. Okay, so one thing about this is we know that the domain of x is all real numbers. Then in this case right here, how about x to the power of 2/3 then? Okay. Now in this case right here, you could consider that x to the power of 2/3 is x to the power of 1/3 raised to the power square. Okay. Then we know that the domain of x to the power of 1/3 is actually all real numbers. So basically, the domain of the function b is all real numbers then. Okay, so meaning what the function basically is continuous. Okay. Anywhere. Okay, from negative infinity to infinity. But one thing about this is we know that when we take the derivative, we have this one right here is actually undefined, right? When x equal to 0. Okay, so it's actually give me the idea that maybe we have a sharp corner here then. Okay, anyway, then let's see the side charge. Okay. Okay, so then now to this one, what I need to do is I'm going to plug it in some number now. Okay, so I could plug it in -1 here, and then to this one, maybe we could plug it in 1 here, and then to this one, we could plug it in 27. The reason that I choose 27 because we need to work with the Q root. Okay. Okay. So anyway, so if we have -1, so basically we will have 2 over Q root of -1 minus 1. Okay. So we know that this is a negative. So here the whole interval is negative. Then now I will have 2 over Q root of 1 minus 1. That is 2 minus 1, which is positive. And then now the last one is we have 2 over Q root of 27 minus 1. Then this is 2 over 3 minus 1 is negative. Okay. Okay. So then in this case, we have it now again to this one. If we look back to the 0 and then 8, if we look it back to the original function b, because to the derivative it is negative, meaning what the interval is decreasing. Between 0 and 8 is positive, meaning the interval, okay, between 0 and 8 is increasing. And then it's negative, is decreasing, right? So therefore, from decreasing to increasing, that means this point must be my local minimum. And then from increasing to decreasing, this will be my local maximum then. Okay? Okay, so keep that in mind then. Okay, anyway, then let us try to answer A. Okay, so increasing and decreasing. So to this one, we will have decreasing is in between negative infinity to 0, union h to infinity. And increasing is between 0 and h then. Okay. Okay. Then now, we are going to work with the local maximum and minimum now, right? Okay. Okay, now remember values, meaning we are looking for the output. Then from the side charge, we know that my local maximum at x equal to 8. So, and b of 8 will be 3 times 8 to the 2/3 minus 8. Right? Then it is 3 times 2 to 2/3, 2 raised to the power 3. So I will have this one is 3 times 4. So basically, I have it 4. Okay. And then now, how about my local minimum now? At x equal to 0, then b of the 0 is equal to is equal to 0. Okay. So then in this case, I actually have a local maximum is 8, 4. And then my local minimum is 0, 0 then. Okay. Okay. If I answer values, the local maximum value is equal to 4. Local minimum value is 0. Okay. Then C is find the interval of the concavity. Okay, so then now we need to work with C. And the inflection point, right? So what we need to do is we need to find the b double prime of 0 is equal to 0, or b double prime b double prime of x is equal to undefined. Okay, just like what we found the critical numbers. Okay, then now to this one, we actually seeing the b double prime of x is -2 over 3 times x cubed of x. Then we know that it's only when x equal to 0 is actually is will make the b double prime as undefined then. Okay. So and now we need to work with the side charge again. Now remember this side charge is work with b double prime, and then the number here is the 0. Okay. And then now what we need to do is we could plug it in -1 and 1 here, okay, to test, right? Then of course, if we have -1, then this is negative. If we have +1, this is also negative. Okay. Now remember the second derivative. How is this compared to the original b functions? If it's negative, meaning this is actually is concave down, and then this is also concave down. If it's positive, meaning concave up, right? So therefore, in this case right here, because we didn't change the sign, so in this case, we do not have any inflection point then to this graph. Okay, so to concave up, we have no, and then concave down, it will be from -infinity. This is 0 right here. To 0 union 0 to infinity. And then of course the point of inflections or inflection point is actually, again, we don't have any then. Okay, so then now the last step is we are going to actually sketch the function now. Okay, so again, okay, so then we're going to have a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. So what I'm going to do is I would like to work with the first derivative. And then remember the first derivative basically is we have a local minimum at 0, 0. And then we will have a local maximum at 8, 4, right? So, okay. And 1, 2, 3, 4. Okay. So this is my local maximum. Okay. And then now what I'm going to do here is I would like to, again, using this one, the first derivative. We know that this function right here is continuous from -infinity to infinity. And then the function is decreasing from -infinity to 0. Okay. And then the function is increasing between 0 and 8. And then the function is decreasing between 8 to infinity. Okay. So I'm using a strict line to actually help me to guide my functions. And now, what do we have here is, I have concave down between infinity, -infinity to 0, and concave down between 0 to infinity. So therefore, in this case, my graph, okay, probably is something like this. It is concave down. And then it is concave down. Okay, my local maximum is here. Okay. Yeah, probably this is my graph now. So then this is my E of x. Okay, so this is how we sketch the function then. Okay, so now it is your turn to actually to work on number 4. Okay, now to this one right here, we know that to this function right here, we have a rational functions. So to the vertical rational function, we have like vertical and horizontal asymptotes. Okay, and then just like the previous example, then we would like to find the interval of increasing and decreasing, local max and min, okay, and concavity and inflection point, okay? And then the last thing is we sketch, okay? So again, just like before, we would like to first take the derivative, first and the second derivative, okay? But before we do this, then we know that the domain of this function is all real number except x equal to 2, right? Okay, so now then maybe let us again try to take the first and the second derivative, and then we are going to use like the limit, right, to help us to locate the vertical and the horizontal asymptotes. Okay, so anyway, let's begin. Okay. I would like to factor out the 2x, x minus 2. Okay. Then I will have x minus 2, then minus x. And of course, and x minus x is equal to 0. Then now I will have negative 4x over x minus 2 to the cube. Okay, then now let's take the second derivative now. Okay, so for this one, you know that the common factor will be x minus 2 to the square. Okay. Okay, so then I will have negative 4, and then negative 2x minus 2. And then maybe we could take out -2 here. Okay, so then now we find our first and the second derivative. Okay, so then now remember A, we would like to find the vertical and horizontal asymptotes, right? Then let's see. We know that my vertical asymptote is at x equal to 2. Okay, we know this. Okay, so then I have my vertical asymptote is x is equal to 2. Then now let's try to use the limit to help us to see how the function behave, right? From the left. Okay, so remember, how do we do this? If it is from the left, meaning what we plug it in about 1.9, okay? So again, you will see that if I plug it in 1.9, this is positive, meaning this one will go to positive infinity then. Okay. So same thing. We would like to find the limit as x approaching the 2 from the right. Okay. So in this case right here, we actually approaching the 2 from this side. So about 2.1. Okay. So same thing, it is positive over positive. So meaning this one will be positive infinity. Okay, then now, how about the horizontal asymptotes? So we will take the limit x approaching to infinity of x squared over x minus 2 to the square. Then in this case, we multiply top and bottom by 1 over x squared, right? Then now it is the limit x approaching to infinity of 1 over this one. Basically, it will be 1 minus 2 over x to the square. Then, of course, in this case, we found out that the answer is equal to 1. Okay. So then, because again, this goes to 0, right? My horizontal asymptote is y equal to 1. Okay. Then now, we would like to work with the increasing and decreasing. So we need to work with the side charge now. Okay, so then now I have f prime of x equal to 0, or f prime of x is undefined, does not exist. Okay. Then of course, to this one, we know that x is equal to 0 and x is equal to 2, right? Okay. Okay. And now, remember in this case, x equal to 2 is a vertical asymptote. Keep that in mind here, okay? And then now, what we're going to do is we work with the side charge. So I would like to choose a -1, 1, and maybe 3. Okay. So if I plug it in -1, so this is positive, and then this is negative. So it's turned out that it is going to be negative. If I plug it in 1, so I will have negative and over negative, so this is positive here. Then if I plug in 3, so I have negative over positive, so this is negative right here. Okay. Okay, so maybe let me move it down a little bit. Too close. Huh? Okay, do it again. I have 0, I have 2. This is f prime. I'm choosing negative 1, 1, and 3. Okay, so remember this is my vertical asymptotes. Okay, so as before, then we again this is negative, positive, negative. This one will be plug-in 1. I have negative, then negative, and then plug-in 3. I have negative, positive. Okay. Then now you know that again from decreasing to increasing. This one is my minimum, and of course this is my vertical asymptote. So we need to do this. Okay. So then now it is decreasing. It's actually is from negative infinity to 0, union 3 to infinity. Increasing is between 0 and 2. Oh, this is 2 right here. Okay. Okay. Then now I would like to find local maximum mean. So then to see, so I have one local minimum at x equal to 0, and we know that f of 0 basically is equal to 0. Okay. So then I have 0, 0. So my local minimum value is 0 then. Okay, then now D is the one that need to work with the concavity. D, we would like to find the concavity and inflection point. So we need to work with the f double prime of x equal to 0, or f double prime of x does not exist, right? So again, to this one, when x is equal to -1, again, we look at the second derivative, okay? And when x is equal to 2. Okay, then now, -1, 2. This is my second derivative. Then choose a test point. Then maybe we could choose a -4, 0, and 4 then. Right? Okay. Okay, so if I plug it in, work with the second derivative, then if I have -4, then I will have negative, and then the bottom is always positive. So this interval is negative. And then to the zeros, then I have positive, positive. If I have 4, positive, positive. Okay. Again, remember this is my vertical asymptotes right here. Okay. So I only have one changing from the concave down to concave up, and also concave up here. Okay. So therefore, okay. Okay. So then concave down is in between negative infinity to -1. Concave up is from -1 to 2 union 2 to infinity. And of course, my inflection point is at x equal to -1. F of -1 is equal to -1 to the square over -1 minus 2 to the square. So it's just 1/9. Okay, so now we have everything, and now we are going to sketch the function now. Okay, then what we need to do is we are going to have a scale. Okay. First of all, we have a horizontal asymptote. Okay. We also have a vertical asymptote at x equal to 2. We know that to the vertical asymptote is go to positive infinity, right? From the left and from the right. And then what else? Okay. So we know that we have one point is 0, 0. This is my local minimum. Okay. And now we work with the first derivative. Then I have decreasing, increasing between 0 and 2, and decreasing again. Okay. So therefore, in this case, then now we will have decreasing, increasing, and decreasing. Okay. Okay. So then now at x equal to -1, we have a point of inflections here, or inflection point. Okay, so then now we have again, let us finish the graph now. We have a concave down here, and then we have a concave up. Okay. Concave down, and then concave up, and then there's concave up. Okay. Okay, so then this is what we have now. Okay, and this is my function f. Okay, and my horizontal asymptote y equal to 1. My vertical asymptote x equal to 2. Okay. Okay, so that is it for these sections. Okay, so again, this section right here basically is using the technique that we have learned from the first package. Okay, the first and the second derivative test. Okay, and also using the technique that we learned from chapter 3, right? Using the first and how do we take the first and the second derivative of the functions, okay? And then gathering all information together, and then we graph the functions. And of course, we also introduce the mean value theorems, okay? Okay, so that is it for this lecture. Thank you.